Hello guys, today the topic that you're going to learn is to use VIVADO HLS to also synthesize IP cores which has BRAM interfaces. BRAM stands for block RAMs, are really fast memories that you can have inside your FPGA, and basically we're going to learn how to use IP cores that read and write on those blocks of memories, and also learn how to make those memories inside your FPGA to be available to the PS part of your Zynq, or really be a memory addressable by your CPU. Okay, hope you guys like it. This theory I'm going to spend a little bit of more time, because it's not more difficult, but it's nice to talk a little bit more, and then in the end I go to the lab and show how to do this in real life to see how to do this. Okay, I hope you guys enjoy it, and let's start. So, BRAM on Axie. Okay, BRAM stands for block RAMs, are really fastest memory that you have inside your FPGA. So it basically is the fastest way to get data in the FPGA, because for instance, if you use DDR3, you're going to have a controller of the DDR3 who is going to pass the memory. But block RAM nodes are the fastest way to have memory on the FPGA. Unfortunately, you don't have too much, okay? You don't have like megabytes of RAM. You probably have 1 megabyte or 1 dot something, okay? So, how we access the block RAM for our microcontroller or Zynq or Microblaze or whatever, okay? You have the BRAM generator IP core. You need to use this guy here, the Axie controller, the Axie BRAM controller, which is going to allow the Zynq or Microblaze to see the BRAM mapped into the Zynq, into the ARM memory space. Okay, those block RAMs can have multiple ports, so you can have, for instance, your microcontroller reading data from the BRAM while you have an IP core that is writing data to the BRAM. Okay, so we're going to see how, with more detail, how to do this in the lab. Okay, guys, VIVADO HLS BRAM interface. So in our lab, we are going to synthesize a core that is going to implement this function here. Okay, it's going to calculate the sum of x plus the square root of the exponential of y, and all this divided by 2. Okay, this has no meaning at all. It's just a crazy function. It's just to show again how to create floating point IP cores. Okay, the input of this function is going to be a vector that is going to from 0 to 100, okay, to 9999 to 99, okay, and after this block is done, okay, it's going to be to generate an IP core that has an Axie-like interface, which we're going to set our y value, okay, and two BRAM interfaces, one BRAM for the input vector and one BRAM interface to the output of the function. Okay. So, as I mentioned in the introduction, these guys are going to be connected to a block RAM generator. Okay. And in order to our Axie-like, or to our IP core to have access to those block RAMs, and our Zynq as well, we're going to use the Axie BRAM controller, which actually maps into the Zynq memory your block RAM. Okay, just to mention, the interfaces used to communicate with the block RAM will be Axie full. So it allows burst. Is one of the fastest way to communicate data from your program to the FPGA. The problem though is that the block RAM in the FPGA is quite limited. You don't have like megabytes of RAM. Okay, I'll post on the lab how much RAM we're going to have in the Zynq. Okay, so guys, Zynq interconnect all the Axie blocks that are going to be available to our Zynq is going to be used for this interconnect. We are going to use the general port master, the GP master port of the Zynq. And well, we're going to use also an Axie timer there, just to count the time and see how well we went or not. Okay, so well, I think this is enough. We are ready to jump to the lab and see how this works. Okay.
Hello guys, so let's start our lab. Is the lab 6 HLS BRAM. Okay, so as we said uh, on the board, we are going to create a simple IP core, again float point. Okay, so well, basically after the project is created, the idea is to create our IP core main source code. Let's call it for instance core.cpp. Okay, well, the main idea of this lab, beside creating this crazy function with these mathematical results, is also to use the BRAM interface. So what do you mean? This function will receive a vector of 100 elements, okay, and one of the parameters y will be used to calculate an exponential, but this will be held as a constant. I mean, we are not going to use a vector in y, and the result will also be a vector with the same number of elements of our input vector. Okay, so in this case, x will be allocated on the BRAM, which means the internal memory of the FPGA, which is a very fast memory to communicate because it's basically inside the FPGA itself. Y and the function result will be used in the AXILite interface, because basically we want to know when the function finish running just by reading the AXILite interface, and the result will be also stored in the BRAM. Okay, just by using the BRAM itself does not mean that the BRAM will be available for you on the Zynq. We're going to use an IP core that maps the BRAM to the memory address space of your ARM inside the Zynq CPU, or the Microblaze, does not matter. Okay, we're going to see this after we finish this IP and test and verify if everything is okay. In the Vivado, that we are going to use a dual port BRAM, and one of the ports will be used by the IP core to write or read the results, and the other one will be used by you to input values in this RAM, or output values as well. Okay, just an important point to remember: we are going to use the HLS math functions basically because we want to have the C simulation matching with the HDL simulation regarding the mathematical functions. So this is an important step to begin with. And now we are going to type what the function will do. Again, the parameters are used just to define the interfaces. And yes, let's do this for loop that is going to be from 0 to 99. And well, let's add the code. So by the way, I'm going to put in this balloon message the function, just to help you guys to understand what it does. Okay, so let me just add a comment, and I already jump the part that we're going to put the test bench, but I will show you guys how to test it. It's really simple. Okay. So basically here is the report of the synthesis. As we can see, this mathematical function bites a big chunk of the FPGA resources. If you can see, I will scroll down. It uses 10% of the DSPs, 2% of the flip-flops, and 14% of the LUTs. This, let's say that this is too much just to implement one function. You know, sometimes you use DSPs to create like really fast filters and stuff like that. But the idea of this video today, of this tutorial, is just show how to use the BRAM interface. Okay, in the next videos you're going to see how to improve this, at least in terms of resources and speed on the FPGA. So here are the results on the simulation. Now I'm adding the co-simulation also to check if the simulation with the HDL generated code matches with the C simulation. Okay. So guys, well, as I said, this is the test core. It's really simple. It's just populate a vector of 100 elements, the input vector x. We call our function, call the device under test, let's call like this, and just print the results. Okay, I already run the co-simulation, so let me just open up this. So these are the results of the HDL simulation, you see. And in the beginning we see, let's see if I can, yes, here. So this is the simulation that we did in pure C. Okay, they should match, and they match. Okay, so let's close this or minimize. And well, the idea is now just to package this IP core. He's complaining that we modify a little bit the sources. Yeah, okay, let's run the synthesis again. Sometimes VIVADO asks for this. And well, basically we just finish this. I'll just pause here to gain us time, and we put to package the IP. Okay, so synthesis is done. Now we can go and ask to export the package. Okay, and then we can open as a block in VIVADO. Let's just take a look again in the interfaces. Okay, so this line here simply add an Axilite interface for the control signals of this IP core. So for instance, with this you're going to be able to start, stop, check if the computations are done or not. Okay, this is the Axilite interface for our Y parameter. Okay, also bundle in the same control bus, otherwise every Axilite port will become a different interface. And here is the BRAM interface for the input vector and the BRAM interface for the output vector. So in the VIVADO we are going to connect two block RAMs here. Okay guys, so let's jump to VIVADO. Okay guys, so let's create quickly a new project in VIVADO that is going to use lab, let's call it lab 6. That's going to use Zynq IP. That's going to use our new IP that created through VIVADO HLS that use the BRAM. Okay, so as usual we're going to choose the Z board. So we are going to create a block design. There we're going to add our Zynq. Okay, Zynq. Okay, we run the block automation just to make the connection to the DDR. And from this point, well, we are ready to configure our repository to add our new core that we just created. which is here, solution 1. It should be enough. Vivado will look for the IP. Okay, so now let's add our crazy function. Okay, we can run the design automation, the connection automation. Let's start just by connecting the axis part that we're going to use to set the value of our y parameter. Okay, let me just do a zoom to help a little bit more. Okay, so now if you run the design automation, for instance, for the port A, you're going to see that BRAM block memory generator is going to be instantiated. Okay, this is not enough, because if we do this, the only access to our block RAM will be only through our core, and this is not exactly what you want, because you want the Zynq to also be able to write to this piece of memory. Okay, so what we can do is first to change our block RAM to be true dual port RAM. So we're going to have 2 ports to access this RAM. Okay, we can add an IP called not this, axis block axis BRAM controller. Okay, so the axis BRAM controller now is using two ports. We're going to use just one for the BRAM interfaces. Okay, and the protocol that we're going to use is axis 4. Okay, it can be axis lite, but axis 4 is better because support burst of data, and is a little bit faster than the axis lite. Okay, but in the terms of for the software point of view, will be the same. Will be just an address in the memory that you're going to write, and actually is going to write directly to our BRAM controller. Okay, so let's connect this guy here. We run the connection automation for our BRAM controller. Sorry. Okay, so now this block of RAM will be accessible through axis lite. Oh, sorry, for our BRAM controller that has that is mapped to our Zynq. Okay, here is just being used for interconnect, as I showed in the board before. Okay, so now let's run the design automation just to the connection automation. Sorry, I always forget to create another block of memory generator. Okay, then we're going to configure to have another port. Okay, guys, we're going to add the axis BRAM controller, which does not need to be dual port. It's going to be controlling just one port. Again, the protocol will still be axis, full axis. Cool. Now we control through this guy as well, and we finish by connecting this guy. So if we do a zoom, let me close to show a little bit better the diagram. Okay, so those guys here, which are our block RAM, will be accessible through the Zynq. Okay, through our BRAM controllers, and also through our IP core. Okay, so let's save it. In the address editor, one thing that is nice to notice is that our BRAM controllers have an address. Okay, by the way, if you just create a float pointer to this address, you are actually reading or writing on those guys. That's the whole idea. Okay, so have a look on this address. You're going to use really in some moments. The crazy function as well, as it has an axis lite interface, is going to have an address as well, where we're going to use to set our parameters, start and stop our IP core. So let's just validate our model to check if there is something wrong or not. And well, we are close. Cool, no problem. So let's save, let's reset the layout. Nothing changed, I did not expect that because reset layout. Good. So cool. So let's go to sources. Let's create an HDL wrapper for this block, and you are ready to synthesize. I always make a mistake. Cool. Now we generate bitstream. Yes, and probably wait more 15 minutes or something like this. I will do a pause and I will come back when this is done. So synthesis is done, implementation is done. Let's open the implemented design just to have some idea on how much of the FPGA our crazy function took. Okay guys, so one of the things that we do not discuss it yet, but we're going to discuss in a near future, is timing. Okay, so basically you need to avoid those numbers to be negative. Okay, most important, the hold. Okay, a negative hold slack is a guarantee 100% that the design will not work. A setup negative slack, not so much. Sometimes it's going to be a little bit slow or something like this. But this one, guys, negative, no go. Okay. If you click here, it's going to show in the order what are the most critical paths. Okay. So by clicking here, we can see where they are. Okay. Probably this is not a cross domain, but is jumping from an array to another. This can be a little bit critical. If you press F4, you can see in the schematic where this is. Okay, in this case, it's probably the is the interface, is our BRAM interface. That is the most critical. That is going to some subcomponent of it until our processing system axis peripheral. Okay, if you click on the block and press F7, you're going to jump to the HDL code of it. Okay, but going to talk about this later. Okay, so now that we know more or less, let me just jump out. Okay, in the net list, let me just highlight our crazy function stuff with a different color just to show. Okay, so you can see, guys. Okay, in the project summary we can see some statistics about our project. Actually we use 9% of our DSPs, 10% of our LUTs, okay, our logic units, and this is basically our crazy function. Okay, well, after this is done, I will just now I can connect this to my Z board and open the Zynq SDK. So we export the hardware. Okay, and we can launch SDK. I'll launch it anyway, and I'm just going to connect my Z board. Okay. Okay, guys. So this is the Zynq SDK. I have already a project that is going to run this IP core to test. So basically, we have a header that is going to point to our generated driver from the VIVADO HLS. Okay. Detail: this driver is just created for AXI-Lite interfaces. Okay. AXI masters, I'm not sure, but for sure AXI stream or BRAM IPs alone, no. Okay. So first thing, we create some pointers that actually map into the address that, okay, while it's running, let me go back again to the addresses where we have our BRAM controllers. Okay. Then we have the two variables that are going to use to instantiate our IP core. Here is the function that is going to do this in each crazy core. So basically we do this lookup config with this guy here, which is defined in the parameter files. By the way, let me just show if needed. Open declaration, X parameters, okay? It's good to put here X parameters as well. It will run anyway because it's kind of global, but it's nice to have. Include X parameters, cool. Okay, then we use the function cfg initialize with a pointer to our do crazy function and to our config that we initialized in the previous step. Here is the same function that I just copy and paste from Vivado HLS. For sure I took out the HLS prefix, but it's basically the software version of the IP core that we have. This function I mentioned before is a function that is going to use to convert float to the IEEE 754 representation, which is the one that is used in memory to represent the float values. And our main function is quite simple. We just init our cores. We also using the axis timer here just to measure a little bit of the time and see how stuff goes. And quite simple. We just initialize our vector from 0 to 99. We start the timer, call our function, and stop the timer. And here we just calculate how long it takes to execute. And here is the same thing, but now using our IP core. So we set the value of y, we start the timer, we start our function, and we wait while the function is not done. When it's done, we stop the timer. Then we get the elapsed time, okay, and we print some the time that took to execute the function. Then later we just calculate the total amount of error, okay. Let me just run as it is. I ran it before, so actually you guys will see no difference. So the software version took 162 microseconds. The hardware version a little bit less, 1/3 less, I would say. And the total average error is 0. If we print out the result of software and the result in hardware, we can see this by running again. So they're really the same. Okay. If you found the error, maybe is in the far away decimal case and stuff, but it's the same. Let me just run this guy here in debug mode just to show you guys a nice okay, just to have the function nothing in the memory. Just a brute force stuff. But so let's run until that point and do the start. Okay, so step over. You see, guys, basically it really how could I say, independent of the ARM processor, the execution of the function. Okay, it's like all those values here got calculated really in parallel. It's kind of magic in the software point of view. You're just going to get the values there independent. I mean, you could really do anything else. For instance, this guy have an interrupt that you could use here in the Zynq. I will show you guys how to enable this interrupt. It's quite easy. And then really you just create an interrupt vector. This is, by the way, something that we're going to cover in the Zynq training. So fabric interrupts, PL to PS. Okay, so we just connect the interrupt here, and really you could continue our program, do whatever you want. If the speed of the IP core still does not match your requirements, you could just come here and pump up a little bit more this frequency, okay, if you want to be faster. And well guys, I think this is good for today. Just something that I forgot. Here is our Axie BRAM controller's address, and they match exactly with our pointers here. Okay, so guys, hope you guys enjoyed, and let's close this video. Next video we're going to talk about creating IP cores that use Axie Stream and Axie Lite together. Okay, so see you guys, bye bye.